Welcome everyone to this afternoon session on post-quantum crypto. We have 5 papers and 4 talks in this session. And this first talk is going to be about post-quantum simulatable extraction with minimal assumptions, black box and constant round. And it's authored by Naihori Chia, Kaimin Chung, Xiao Liang, Takashi Yamakawa. And Xiao Liang is going to give a talk. Maybe we want to...
We don't hear the speaker.
Hello. Yeah. Hi, everyone. I'm here to share our results on post-quantum simulatable extraction. This is joint work with Naihori Chia, Kaimin Chung, and Takashi Yamakawa. Okay. The last name of Kaimin ends with CHUNG. So I did it on purpose, so you won't forget he's one of the co-authors. Okay. So I want to start with the extractable equivalence. I think everyone here knows what it is, but I just want to make sure that we agree on the same definition. And there's something I want to address. So let's focus on statistical binding commitments for now. Such a commitment scheme is extractable. In the following sense, we will compare 2 words. The first word is nothing but the real execution between a potentially malicious committer and the honest receiver. At the end of the execution, we denote the final state of C star as ST C star. And the B is a binary bit indicating if the receiver accepts or not. The tran denotes the transcripts all the messages exchanged between them. In this real game, we will focus on this tuple. ST C star and B is pretty straightforward. So I want to define this value. While tran, this value statistically bound in the transcript. Okay. So we compare this game with a simulation extraction word, where we replace the honest receiver with SE, which is a simulation extractor. And the job, by the way, the simulation extractor could potentially rewind the C star, and it's trying to simulate this tuple. It's trying to simulate the final state of ST C star, meanwhile extracting the committed value until the out. So this scheme is extractable if there exists such an efficient SE, make these 2 tuples indistinguishable. Here, the thing I want to address is usually in the classical setting, we care more about extraction. But here, I explicitly require that the extractor also simulate the final post-extraction state of the malicious committer. Let's first take a look at a very typical construction for extract commitment in the classical setting. This scheme, again, I think everyone knows that. So to commit this value M, the committer pick 2 random string, A10 and A11. They basically form a 2 out of 2 secret sharing of this message. And he repeats this procedure for n times, where n is the security parameter. Then he commits to these random shares independently. You'll say NAR commitment. Next, the receiver select a random string of length n and give it to the committer. The committer will decommit accordingly. So this construction is very popular in the literature. You can find it on basically any zero knowledge or MPC paper, but it got popular for some reason. It enjoys these good properties. First, it makes only black box usage of the underlying assumption of which is a one-way function. The reason is you can get the NAR's commitment in black box from one-way function. And to do this, you only need a commitment. So you have a black box construction from one function eventually. And also it's constant round. These 2 properties are very important for efficiency concerns. The third one is like we usually take it for granted in the classical setting. But I want to say that it's very important for a protocol composition purpose. For example, if you want to use this scheme to build something else, for example, coin tossing or 2PC, it's a gadget appearing in the middle of your protocol. You want to make sure that after extraction, the final post-extraction state remains close to the reward, so that you can use composition lemmas to simulate the remaining parts of the protocol. But this, why I say it's take for granted, because in the classical world, you can just, if you want to build an extractor, your extractor can just behave like the honest receiver, finish the real execution straight line. And then you learn the final state of a potentially malicious committer. You just record this number or record the state. And then you rewind the execution back to right after the first message. And then do whatever you want to perform the extraction. In this way, you can finish your extraction and get the post-extraction state easily, right? However, I want to mention that this procedure is typically hard in the post-quantum setting, meaning if the committer is a malicious quantum machine, because in that case, because of the no-cloning theorem, you cannot do what I just said in the classical setting. If you finish the protocol, learn and record the final state of the malicious committer, it's hard to run it back and extract the information out, right? So let's take a look at the state of arts. If we want all the good properties shown earlier in last slide, basically there are 4 known constructions. You can see that only the last one achieves a black box construction, and only the second one achieves constant rounds. In this column, I also show if the honest parties to execute the protocol need quantum power for computation and communication. And here are the assumptions. You can see that the first construction needs assumptions as strong as oblivious transfers. And the second construction, which is very elegant, but it uses a little bit heavy tools like fully homomorphic encryption for quantum circuits. Yeah. So it looks like the state of art is not that satisfactory, but actually there is a reason. This problem is hard even if you only require these 2 properties. The reason is such a commitment with these 2 properties will imply constant round zero knowledge in the post-quantum setting, for which we have negative results. Due to time limit, I won't explain these conditions. If you're interested, you can find this paper in our reference. Yeah. So what do we do now? Because we cannot get everything we want shown here. And these things we don't want to give up because they are good properties for efficiency purpose. You want to use minimal assumptions. So eventually we choose to relax the security goal. We relax it to something called epsilon simulation. There are 2 words. These are just the 2 words I showed you on the second slide. Previously, I require the distributions of the output are computationally close. Here, I change this sign. In this definition, I will give a noticeable function epsilon as a parameter or input to the simulation extractor. The requirement here is as long as you fix a epsilon, give it to the simulation extractor. The simulation extractor's running time will depend on this epsilon. However, it can simulate to epsilon up to an epsilon error, or for whatever epsilon you pick. So this is okay, for people who are familiar with epsilon zero knowledge, I think this is also standard. So, but before going on, I want to mention that epsilon simulation is really useful. It's still useful because a epsilon simulation security usually implies IND-based or game-based security in the sense that epsilon zk will imply witness indistinguishability. So we ask the question, if we are happy with epsilon simulation, can we have a construction achieving all the remaining good properties? In this work, we showed that it is indeed possible. And I think the classical setting, extractable equipment is a very powerful primitive. You have that, you can have a lot of applications. And we are just doing the same thing in the post-quantum setting. The first 3 implications are kind of not that hard to achieve. You just do what you will do in the classical setting, but replace the extractable COM with our epsilon version. So I won't really discuss about these 3, but I will, at the end of the talk, I will mention a little bit how we do the last step. All the properties, all the protocols shown here enjoy these good properties, but since our extract COM is epsilon simulatable, so we only managed to achieve epsilon simulatable version for all these primitives. There's something I want to say about the blue error. We know that if you want 2-party computation, the minimum assumption is actually some amounts to OT. But that's like in the post-quantum setting, you require that the protocol honest parties has to perform classical tasks. If you are happy with the quantum computing and quantum channel for the honest parties, you can replace semi-honest OT with the post-quantum secure one function plus quantum communication and computation. So let me talk about our technique. I want to start with a closer look at this classical construction I just showed before, and I want to see if we want to make it, or if we want to quantize this proof, or what difficulties we will encounter. So to remind you how the extractor works, first recall that all these columns of this matrix are the two secret sharing of the same message. So how do you do extraction? You can just rerun the execution back to the second stage and pick a fresh C prime and expect that the C star will decimate to you. As long as there is one position where C and C prime differs, you can recover the M by just XOR the two secret shares of the same column. So this is how we do extraction in the classical setting. Now we want to quantize this proof. You can see that we need to handle rewindings and also extraction simulation in the post-quantum setting where the C star is the quantum machine. We don't have much tools to use actually. You may be able to use the Waters, for example, to handle simulation, but here we are also in a constant run regime. So in this regime, I guess the most closely related lemma is this simulation extraction lemma from a previous work by Cha, Chong, and Yamakawa. So we will take a look at this lemma and see if we can use it in our setting to quantize this proof. Let me first explain what does this lemma say. This lemma is also compared to words. Again, let me first explain the first word. The first word is nothing, but we have a malicious committer, and he performed this commitment stage to commit a value and obtain a intermediate state. He passed this state to the decommit phase. This represents a decommit phase. The adversary just perform the decommitment. And the output of this game is defined as follows. If the decommit is valid, then it is not valid, then we just ask him to return bot. We don't want to simulate anything. However, as long as this decommitment is valid, we will return the value and the commitment randomness together with the final state of the adversary at the end of the decommit phase as the output. So this CCUI lemma says this word actually is epsilon close to the second word. What is the second word? It's the same as the first word, except for the red text. You can see that the only thing we do is we insert here the simulation extractor. What it does intuitively here is it tries to extract the committed value, which I denoted at M tilde, before the decommit phase happens. Meanwhile, after this extraction, he also wants to simulate the intermediate state role. Because in the quantum setting, if you extract something, you may disturb the state. This simulation extractor will extract value and return the original state back to you, even though it's only epsilon close. The remaining steps is the same as here, except for this additional condition. Here, the intuition is if your extraction is not valid, you just output bot. So in this way, we want to enforce that this simulation extractor should extract the valid commitment value. Okay, so you can see that this one you want to extract the value and finish simulation together. And this lemma, in some sense, does this for you. Can we use this lemma in this setting? Oh, sorry, this is just epsilon simulation. It turns out to be that it's unclear. There are basically two obstacles. The first one is if you look at this real game closely, you'll see it considers both commitment stage and decommitment stage. At the decommitment stage, you'll learn the value M explicitly. However, in this world, it considers only commitment stage, and no one will tell you the value M unless you do this extraction by yourself in the classic setting. And in the quantum setting, it's not even clear how you can do that, right? And the second issue is But this is a commitment. So if it's statistically binding, as long as you have this commitment, there is a unique value bounded in the commitment. But this commit stage is more like flexible. I said that all the columns should be the XOR of the, it should be XOR to the same message M. However, the malicious C star may not follow the protocol. So maybe he finished the execution, but there's no M well defined. This represents the two obstacles. Because of that, it's actually unclear how you can use this lemma. So we will address these two obstacles one by one. We start with the second one. It's about the well-formedness of the committed value. For now, let's assume for simplicity that the C star will cheat in whatever ways, but he will give a consistent commitment here. So let's first address the first issue and assume that the second issue is not there yet. Yeah, but even in this setting, again, because of the problem I mentioned earlier, there's no one that tells you the committed value M. So it's unclear how you can define the machine that gives you M and then use the CCY lemma, at least in a black box way. So we will handle this issue by opening the security proof of CCY and do some non-black box modifications. To do that, I first need to remind you of the security proof. I will give you a very high-level explanation. I omit a lot of details, but I think it captures the main intuition. Basically, if you ask me what is the idea behind CCY, I will say the power of uncomputing. It works as follows. We want to do this extraction and simulation. Given a state rho, we first decompose it by something called Jordan lemma into two portions. The first portion represent the state in the superposition where the decommitment algorithm will tell you the correct decommitment with probability greater than epsilon. The epsilon is you defined before because you want epsilon simulation. Now the second part is just the portion where this decommitment algorithm responds to you with probability smaller than epsilon. Now, if we do this decomposition, there exists a unitary operation which we call amplifier. It works in the following way. When you apply it in rho, it applies to these two portions separately, independently. And it will amplify the response probability in this greater than epsilon portion to overwhelming. But on the second smaller than epsilon part, we lose control. We don't know what's happening there. However, the main takeaway is that it will work on these two branches separately. It won't get mixed. So this algorithm you can take for granted. And let's say if we have this algorithm, what do we do next? Next is you just apply this decommit algorithm on the state you obtained in the second phase. Let's analyze the behavior for these two branches separately. You can see that for the first branch, the decommitment algorithm responds to you with probability overwhelming. So you can extract M from there. However, for the second part, as I said, we lose control. So, but for this one, we don't care about it because we are only targeting the epsilon simulation. After this step, we at least learn the M in the good part, and we memorize it. Technically, you can think it we are C-naughted into a new register. Then we can uncompute. Because quantum computing are always reversible. You can view step 2 and 3 as a big unitary operation. What do I mean by revert? You just apply the conjugate transpose. So after this operation, let's look at these two parts. Again, the easy part is a smaller than epsilon part. As I said, we lose control. We don't know what's happening there. But good part and bad part always like independently proceeds. So it won't affect the good part. Then for the good part, what we do is we amplify the response in probability. Then we extract. We already know that he will respond to us with probability overwhelming. Then by something called a gentle measurement lemma, we can extract information from this state without disturb it. I mean, almost a perfect extraction. Okay. So to summarize, what we do is first we use something called Jordan decomposition to decompose it. And then we amplify the response probability in the good part. For the bad part, we just ignore it. Now the real extraction happens at step 3 and 4. We succeed in extraction for the M in the good part at least. Now we do uncompute. The problem I mentioned earlier is that this CCUI lemma have an explicit construction of a machine that will tell you the value M. However, in our in the extractable column I just showed you before, there's no such a machine. So let's look at these 3 steps. You can see that step 1, 2, 3 depend on this secret teller, right? So our hope here is, can we find such a counterpart in our extractable commitment construction so that we can plug it in to this template, replace this decommitment algorithm with it, and then maybe if we follow the same template, we'll get simulatable extraction. So how to do that? The starting point is we look at the classical extractor. This is what the classical extractor does. At least it extracts the value for you, and we want to view it as the secret teller. However, the problem is this extractor works only in the classical setting. If you are in a quantum setting, maybe again you cannot perform a rerun. It's hard. However, fortunately, using the technique developed by Onru for post-quantum proof of knowledge, we actually can finish the extraction, but without simulation. So these results give us a simulationless extractor. It can tell us the value M at least. Now we just use this simulationless extractor to replace the decommitment algorithm in the CCUI lemma, and it will finish the proof basically. The thing here, what happened here is phase first we get a simulationless extractor, and this is sufficient for step 1 to 3. And then this template will take care of the simulation to give you epsilon code simulation. I admit a lot of details, but that's the main intuition behind the construction. If you're interested, please check our full version paper. I solved this problem by assuming the committer's commitment is well formed. Basically, they are consistent according to the real definition of the construction. However, in general, C* could cheat, right? This actually is easy to solve. You just add the zero knowledge to prove all the commitments are performed honestly. But we are also targeting at black box construction. If you use your knowledge proof on some commitments, you are making non-black box use of commitments. However, this issue actually is well known in the classical setting. People developed a very powerful tool called MPC in the head. Basically, it is the black box commit and proof technique, addressing exactly the same setting here. So we just take their method and to make this commit and proof strategy black box. I won't talk about this due to time constraints, but I would say this is a very interesting technique. You should like read about it. And basically, for all the black box constructions in cryptography, I would say 95% of them are using this technique. So you can check our paper. We have a good presentation with it. I want to give you some words. What I told you before is the extractable commitment epsilon simulatable in the standalone setting. However, actually to use this MPC in the head technique, if you want to maintain constant round construction, there will be some parallel repetition of the extractable column. And it turns out that our extract column is not parallel secure, but we did achieve a weak version in the sense that you view all the sessions as happening together. If one session abort, you can think that you don't need to simulate anything. You can think all the sessions abort. This turns out to be sufficient for the MPC in the head technique because there's only a single committer who's committing a lot of things to you. And if one session abort, you can think the receiver just reject. Doesn't need to simulate. But don't try to use this construction in the, for example, parallel zero knowledge setting, because there you would want to simulate other unabort sessions, even though some sessions are aborted. But our lemma won't take care of that. That's actually an interesting open question. So for the application to black box to PC, we basically need to find some compilers, but there are like a lot of compilers in the literature, but we have restrictions. We want black box and constant round construction. This CDMW09 is a TCC paper. This one is a black box and constant round. It takes 7 ounce OT plus a special commitment ideal functionality. I will give you 7 ounce OT. And this special ideal functionality, actually, it was implicit in the ancient literature. I shouldn't say ancient old literatures, but it just got abstract out by recent work, GLSV21. The reason is these previous competitors, they are more focusing on the UC setting. They claim the standalone setting, but they didn't really provide enough details. And I think this is the first work get this part explicit and rigorous. Once you have malicious 2PC, there is a black box constant round compiler to compile it into a 2PC protocol. So what we show here is our epsilon simulation simulatable extractable commitment can be used to implement this ideal functionality. So we have the final result. This is something I already showed you before. If you are happy with quantum communication, then you can take one function, and this will give you some ounce OT. It's an alternative approach to eventually reach 2PC. So finally, I'll mention some concurrent work. There is a recent work by Alex Lombardi and Fermima, Nick Spooner. They also achieved epsilon simulatable extraction commitment. And the difference is they give a new and very powerful notion for a simulated running time. That is what they call coherent expected QPT time. This notion is strong. It implies epsilon simulatability. The difference is their construction non-black box, and they need super polynomial harness of one function. Another application of our result is our extractable com plus the recent work by Bitansky, Lin, and Schmeli will give us the first log star lambda round post-quantum non-malleable commitment from the minimum assumption of one functions. And in a little bit more detail, BLS21 actually give us a compiler going from any K round post-quantum extractable commitment to the K times log star lambda round post-quantum non-malleable com. And our post-quantum extractable commitment can be used here. Here is the caveat. This compiler requires a negligible closed simulation for the post-extraction state of the malicious computer. However, since non-malleable commitment is essentially a game-based definition or IND notion, so in the same sense as epsilon not implies witness indistinguishability, you can replace the fully simulatable extractable commitment with a epsilon simulation version. And I will take the last seconds for to give an advertisement. You can see that now we have a log star lambda around the construction for post-quantum non-malleable commitment. Can I hope to achieve constant round? Actually, this question was pretty hard in the classical setting even, and it took a lot of effort to go from log star lambda to constant round, because even though in terms of round complexity, the gap may not be that large, but they took totally different techniques in the classical world. So are we going to run into the same trouble in the post-quantum setting? And I have some good news for you. And there is a recent work by me, Omkan Pandi, and Takashi Yamakawa, and we built the first constant round post-quantum non-malleable commitment from the minimum assumption of post-quantum one functions. And if you are interested, you should check this link. And that's all I want to share. I'm happy to take questions.
Thanks for this talk. We have maybe time for one quick question. Is there any question in the audience? I don't see any questions in Zoom, so then let's join me and thanking the speaker again. And while the next speaker sets up, I can read you this very long title. This is actually a soft merge of two papers. The first paper is "The Gap is Sensitive to Size of Pre-Images. Collection property doesn't go beyond quantum collision resistance for pre-images bounded hash functions." There was the first paper that's by Xu Jiao Zhao, Wei, and Wei Tiu. And the second paper is a much shorter title, and it's called "New Constructions of collapsing hashes. And it's by Mark Zandri, and Mark is going to give the talk. So whenever you're ready, please go ahead.
We'll cover that meeting, the meeting. All right, yeah, so this talk will cover two recent works seeking to understand the security of hash functions in a quantum world. Okay, so let's start with the notion of classical collision resistance. So here we have a compressing function that maps large inputs down to small inputs. And we want that despite it being compressing and there being a lot of collisions that exist in this function, that it's nevertheless hard for a computationally bounded adversary to find one. Okay, and this ability to compress inputs while still computationally hiding any collisions has tons of applications throughout cryptography and has made collision resistance one of the fundamental cryptographic building blocks. So the natural question is, when we move to the post-quantum setting, what type of security do we want out of our hash functions? And the boring answer is, why don't we just insist that when we talk about computationally bounded adversaries, we allow them to be quantum adversaries now, so efficient quantum adversaries. And we ask that, it's hard for such an adversary to find a collision. So I'll call this notion post-quantum collision resistance. And unfortunately, this is not necessarily the right answer. So let's see why. This is well known by now. So let's consider one of the canonical applications of hash functions, which is to give us commitments. I'm not going to worry about hiding, because hiding isn't too interesting in this setting. And I'm just going to focus on binding. So I'm going to think of using a hash function to give a binding commitment to a message. And why might you want to use a hash function? Well, maybe you want your commitment to be small. So I'm also not going to define what the security of the commitment scheme we want, but at a minimum, the following game should be hard. Whatever definition of a commitment you want, you would at least hope this game is hard, where the adversary first sends over a commitment. Then at some point, the game gives them a random message, and they have to somehow open the commitment to a random message. So by open, I mean come up with a random coins R such that the commitment is H of M R. So this should definitely be hard if you're going to use your hash function as a commitment. Well, unfortunately, it turns out that that the notion of collision-resistant hash function, upgraded to the quantum setting to be post-quantum, is not enough to guarantee that this commitment is binding. And in particular, Ambanis et al., what they show is that there exist collision-resistant post-quantum hash functions such that they are not binding when used as a commitment. With the caveat that this is relative to an oracle, so it's not a standard model separation, but it, at least shows that you won't be able to prove, say, a black box that the hash function is a good commitment in this setting just from its collision resistance. All right, so what's the intuition? I won't go into the proof, but the intuition for why this is the case is that if we're trying to prove a reduction, we have an adversary that, say, breaks this binding notion for commitment, we somehow need to construct a collision. But this binding notion only gives us one preimage of a hash function. Where do we get a collision from? Classically, we can actually complete the reduction and get a collision. And basically what you do is you run the adversary twice using what's known as rewinding. Unfortunately, as was alluded to in the previous talk, rewinding is known to be problematic quantumly. This has to do with the no cloning theorem in quantum mechanics. And what the Embanis et al. Result does is it really shows that not only is rewinding problematic, but there are cases where it is just outright impossible. So instead, Unruh in 2016 proposed the following notion for collision resistance that's called, or sorry, the following notion of security for hash functions that's called collapsing. And here's the game. So the adversary gets to come up with a superposition of inputs. They send it to the challenger. And the challenger does one of two things. Either they just measure the superposition of inputs and send back the resulting collapsed state, which will just be a single classical input. Or they measure not the input itself, but the result of applying the hash function to X. So on the right, what the resulting state is it's a superposition over all preimages to the hash function that map to the given output. So rather than just being a single classical string, it's this collision, or it's this superposition. Nevertheless, what collapsing demands is that these two cases are indistinguishable. Okay, so this might seem like a bizarre notion for a hash function, but the intuition is that if you thought of H as being an injective function instead of compressing, with an injective function, if you were to measure the output, it actually would fully collapse the state to a single preimage, just because every output has at most one preimage. So in some sense, what collapsing is saying is that in some quantum sense, a collision or a collapsing hash function is as good as an injective function, which is some way of thinking about what classical collision resistance was also. All right, so this is the definition we're trying to achieve. I won't spend too much time on it because it turns out it's actually not super important for this talk. But the point is that now this is widely regarded as the right notion of security in the post-quantum setting, and it has been shown to be sufficient to lift many classical results into the quantum setting. Okay, so now let's talk about what was previously known. So Unruh in 2016 showed that random oracles are collapsing. This is a good proof of concept. It says, like, if random oracles weren't collapsing, that might suggest that the definition is just unachievable. And then in another work by Unruh and a follow-up work by Jipeng Liu and myself, we showed that we can achieve collapsing in the standard model by going through something called a lossy function, which in turn we can instantiate via LWE. Okay, and then here's another sort of positive result for collapsing. So we showed that if you had a post-quantum collision resistant hash function that was not collapsing, that this would give you some pretty powerful objects in quantum cryptography that have been notoriously hard to construct. And while there have been candidates, many of them have ultimately been insecure. So if it turned out that your favorite hash function was post-quantum collision resistant, but not collapsing, this would actually allow you to solve some long-standing open problems in quantum cryptography. On the other hand, we have this negative result that says, well, at least relative to an oracle, you can't have all post-quantum collision resistant hash functions be collapsing. There will be some negative results. But this is really a frustrating wide gap between what the positive and negative results are. It could be on one hand that all standard model post-quantum collision resistant hash functions are actually collapsing, right? The only negative result we have is relative to an oracle, or some assumptions that have not really withstood the test of time. Or the other possibility is that maybe LWE-based constructions, or in particular lossy function-based constructions of hash functions, maybe those are the only collapsing hash functions we have, and everything else is actually not collapsing. We just really, prior to these works, we really didn't know. Okay, so this brings me to the results. So I'll first discuss the results of the concurrent work by Cao and Zhu. So what they showed is that if you assume a post-quantum collision resistant hash function, H may or may not itself be collapsing, but if you impose a certain regularity condition on the hash function they call almost regular, then you can compile that hash function into a collapsing hash function. And as a corollary, what they show is that the cis hash function is almost regular according to their notion, and therefore you can compile the cis hash function into a collapsing hash function. Now I should note that from a feasibility perspective, going from cis to collapsing was already known, right? In particular, cis and LWE are equivalent under quantum reductions by Regev. And so then you could just plug in the LWE-based constructions of collapsing hash functions. However, the Cao and Zhu result does not use lossiness anywhere in the proof. And so it's really a fundamentally different proof than what was done before, and shows that lossiness is not inherent to justifying collapsing hash functions. All right, so now let me discuss our results. So we show how to construct collision-resistant hashes under any of the following assumptions. The first is what we call semi-regular post-quantum collision-resistant hash function. Semi-regular being our term for some regularity condition, which is somewhat milder condition than the almost regular notion, and therefore more broadly applicable. We show that you can construct collapsing hash functions from the hardness of LPN in certain parameter regimes, which essentially match what we know how to use LPN for to get collision resistance. We can construct collapsing hashes from the quantum hardness of finding short cycles and exponentially large expander graphs. The canonical example of this is isogenies over elliptic curves. This also matches what we know of for getting collision-resistant hashing from isogenies over elliptic curves. And then finally, we show that we can construct collapsing hashes from any optimally secure collision-resistant hash function. Here, we don't require any regularity assumption, but we require this notion of optimally secure, which I'll elaborate on later. And then as a trivial corollary, we get these feasibility results where we get the first post-quantum statistically hiding commitments and first post-quantum succinct arguments under any of the above assumptions. Okay, so let's get into techniques. So both works start from the same theorem, which says that if a function h is post-quantum collision resistant, and it's at most polynomial to 1, so no image has more than a polynomial number of pre-images, then we can conclude that H is collapsing. And the proof is pretty straightforward. So the idea is all we do is we are given this state from the adversary that's a superposition of inputs. We measure it once to get one input. Then we apply the distinguisher, the hypothetical collapsing distinguisher. We measure the result. We actually don't care what it says, we just throw it away. And then we measure the resulting state again and get another X. And the claim is that this gives us a collision with non-negligible probability. Just to get a sense of why this might be the case, let's consider the case where the function is actually 2 to 1. In the 2 to 1 case, we can more or less project down onto 2 dimensions. So suppose x1 and x2 are two colliding inputs, and the adversary gave us a superposition of these. Well, okay, we measure the state, we get x1 or x2. And now the distinguishing measurement is some other measurement in this 2-dimensional plane. And the fact that it actually distinguishes the case where we measured the output versus measuring the input implies that the basis for the state is somewhat far from the basis of x1 and x2. So when we measure the state, we get, say, x1, and now we measure the distinguisher, we're going to move a little bit, at least a little bit away from x1. And then when we measure the state again, there's some non-trivial probability that we'll actually end up transitioning to x2, and that gives us our collision. So we show that this generalizes to higher dimensions. The issue is that the loss in the reduction decreases with the number of colliding inputs, and that's why we can only handle a polynomial number colliding inputs. Okay, so now both works try to extend this result, and we extend it in slightly different ways. What Cal and Zhu show is that you can take a hash function h that maybe now has a much larger input size than its output size. Maybe it's exponentially many to one. But as long as it satisfies this regularity condition, you can compile it into a collapsing hash function. And we show essentially the same thing, but with this semi-regular notion. And let's not worry about the difference between almost regular and semi-regular. They're just some way of saying that the worst case number of preimages is not too far from expected, where what we mean by not too far and expected differ from in the two definitions. So I'll sketch our proof of this theorem. The proof by Cal and Zhu is different. So here's our construction. It's a Merkle-Damgard-like construction. The differences being that we're only going to incorporate a single bit of the message at any point in time, at any stage. We're not going to be able to, incorporate a security parameter, number of bits, or anything like that. And also at every stage, we interleave the applications of the hash function with a k-wise independent function f. The very rough intuition for why this works is that we can show that each stage of this application is at most polynomially many to one on the image from the previous step. So we can apply our theorem from the previous slide to each stage to see that each stage is collapsing. And then it was already proven by prior work that Merkle-Damgard preserves collapsingness. So if we have that each stage is collapsing, then the overall hash function is collapsing. Now, there are some technicalities that make this actually somewhat non-trivial to prove. So one thing is that in order to get the proof to work, we need that every stage uses its own k-wise independent function. And then maybe the more annoying thing is that we actually need to not incorporate even a single bit to the message at every stage. In most stages, we're actually going to incorporate 0 and only incorporate the next message bit occasionally. Roughly, the reason we need to do this is we're trying to control the image size at any given stage. And it might be that every time you incorporate a message bit, you could actually have your image size at that stage grow by a factor of 2. And if you had too many messages in a row, maybe you end up getting your image size to be way too big, and now you won't be polynomial to 1 anymore. So by inserting these zeros, we can show that sort of every time you insert a 0, you decrease the image size a little bit. And then you make sure to decrease it enough that when you incorporate your next message bit, you're fine that you doubled the image size. Okay, so let's move on to applications. So the first application is the sys hash function given here. So the inputs are short vectors x, shorts in L2 norm. And the hash function is specified by a random wide matrix A, and you just evaluate by doing the inner product and reducing mod q for some appropriate q. So what Cal and Zhu showed is that the sys hash function is almost regular in many parameter settings. And we know that the sys hash function is post-quantum collision resistant, following from the post-quantum hardness of various lattice problems. So as a result, you get collapsing hash functions from lattice problems. Okay, so what about LPN hashing? So superficially, LPN hashing looks very similar, except we've changed the norm. So now instead of short and L2 norm vectors, we have sparse vectors as our inputs, and also everything's mod 2 instead of mod q. So it was previously shown that this LPN-based hash function is secure, is a post-quantum collision, or is a collision-resistant hash function under certain LPN parameter regimes. We showed that LPN hashing is semi-regular. So what this allows us to do is then compile LPN hashing into a post-quantum collapsing hash function. All right, what about expander-based hashing? So this was introduced by Charles, Alter, and Goran. And so here we imagine there's some implicitly represented exponentially large expander graph together with a designated starting node. And what they propose as the hash function is you interpret your input as describing a non-backtracking walk through this graph. And you just follow the walk, and whatever node you end up with is your output. Right, and so the collision resistance of this hash function follows from the hardness of finding simple cycles in this graph, which could be posited. This problem could be posited hard for things like the graph of isogenies over elliptic curves. So what we observe is that prior work already showed that non-backtracking walks on expanders will mix. And that just immediately, basically trivially shows that this expander-based hash function is semi-regular. So then again, plugging into our compiler, we have a semi-regular hash function, collision-resistant hash function. We can compile it into one that's collapsing. All right, and then finally, let's talk about optimal collision resistance. So we define optimal collision resistance as being any polynomial time adversary. The probability that the output of collision is at most polynomial divided by 2 to the n, where n is the bit length of the range. Okay, and note that random oracles, for example, are optimally collision resistant both classically as quantumly for different for different values of the polynomial. So what we show is that if the domain is not much bigger than the range, say you add log bits to the domain, and if H is optimally post-quantum collision resistant, then H is actually also collapsing. And the proof is not too hard. The observation is that if you have optimal collision resistance, what it means is that maybe there do exist X or that collide with exponentially many points, but it's actually hard to find. Because if you could find an X that collided with too many inputs, you would actually be able to break the optimal collision resistance. So, so it's hard to find X that collide with too many inputs. And then we can more or less use the same analysis as in the polynomially many to one case to conclude that the hash function is collapsing. Okay, and that's basically it for the talk. So I guess the takeaway from this is collapsing is perhaps more prevalent than previously thought. Really, before all we knew was collapsing from LWE or idealized models. And here we showed a number of new ways to build collapsing hash functions. And essentially what we have matches all of the known post-quantum collision resistant hash function feasibility results. So most of the assumptions we have that can build collision resistance and withstand quantum attacks will now also give us collapsing hash functions. And that's it. Thank you.
Thanks for the nice talk. Are there any questions? Okay, I don't see any questions here or in Zoom, so let's thank the speaker again. And while they switch the slides, the next paper is called Statistically Sender Private OT from LPN and De-randomization by Nir Butansky and Sapir Freizeit. And Sapir will give the talk. Do you maybe want to full screen this or?
Yes, here and also here. Okay, hi everyone, my name is Sapir, and I'm going to tell you about statistically sender private oblivious transfer from LPN and de-randomization. And this is a joint work with Nir Butansky. Okay, so just before I start, let me tell you about the work in a nutshell. So the main goal of the work is to expand our reach of the learning parity with noise assumption, or LPN in short. And we focus on two methods: statistically sender private oblivious transfer, which is an oblivious transfer protocol where we really take the round complexity and the security to the extreme. And the results we achieve is, first, we construct an SSPOT protocol in the common random string model from LPN. And then we remove the CRS using the standard Nielsen-Wigderson style de-randomization assumption. Okay, so the talk is going to be divided to two parts. So in the first part, I'm just going to give you a brief overview of the work and the definitions, and then I'm going to dive into the construction itself. Okay, so first of all, let me tell you about LPN. So LPN is the problem where, first of all, everything is over the binary field here. And we are given a random binary matrix A, which indicates a random binary linear code. A is long matrix. And our goal is to distinguish between the case of when we are getting a noisy code word or just a random vector in the space of all code words. And the assumption says that for every computationally bound adversary, it's hard to distinguish between the cases. So LPN comes with, so the noise of the code words is distributed IID Bernoulli. And we have a parameter epsilon, which indicates the noise rate. So as long as epsilon is bigger, the problem gets harder. Okay. So whenever we talk about LPN, we should keep in mind its twin problem LWE, the learning with errors assumption, which is defined exactly the same, only that we work over a larger field FQ for some large Q, and the error is distributed discrete Gaussian instead of Bernoulli. So both problems are considered to be hard and resilient to quantum attacks. But although they are very similar in flavor, they are very different. And generally speaking, LPN is far behind LWE, both in terms of applications and in terms of known hardness results. So from LPN, we know mostly how to construct pretty basic primitives like public key encryption, secret key encryptions, commitments, and so on. While from LWE, we know how to extract much more advanced primitives like fully homomorphic encryption, non-interactive zero knowledge, and much more. And in terms of hardness results, we know how to prove worst case to average case reductions for interesting noise, for interesting parameters of the LWE problem. And from LPN, we almost know nothing actually. So why do we still want to stick with LPN? Why do we want, So why do we still care about LPN and not just want to stick with LWE? So first of all, LPN has a very high potential efficiency because it only contains simple bit operations. And also, of course, because of robustness, we want to base crypto on as many assumptions as possible. And LPN and NWE, although they are very similar, they're not comparable to each other, and they're just different assumptions. And also, of course, theoretical. The problem of LPN is related to the very long-studied problem of decoding random binary linear codes, which is very interesting. And we want to understand it more. Okay, so the LPN research continues, both in terms of applications and harness results. And our main contribution is in the applications part, where we build the first statistically sender private oblivious transfer from the LPN assumption and an additional de-randomization assumption. Okay, so let me tell you about oblivious transfer. So oblivious transfer protocol is a really fundamental protocol in cryptography, and it consists of two parties, the receiver and the sender. The receiver has a choice bit C, and the sender has two messages M0 and M1. And the common goal of the two parties is to let the receiver learn the message of its choice, MC. We also require two security guarantees, and they are that the sender doesn't learn the bit of the receiver C, while the receiver doesn't learn the other message of the sender M1 minus C. So as most of you know, this protocol is really basic and it's complete for multi-party computation. And we are interested in making it the best possible in all features of interest, such as round complexity, security level, and so on. Okay, so in this talk, we focus on statistically sender private oblivious transfer, or SSPOT in short. So this is an oblivious transfer protocol where we require the minimal round complexity of only two messages, one message from the receiver to the sender, and the second message from the sender to the receiver. We require computational receiver security, meaning that the choice bit of the receiver is kept hidden from any computationally bounded sender. And also statistical sender security, meaning that any receiver cannot learn the other message of the sender, even if the receiver is unbounded. Okay, so formally it means that the first message of the receiver fixes a message that it won't be able to learn. Okay, so we are really taking round complexity and security to the extreme here because it's really the minimal round complexity. And with only two messages, we cannot hope for a statistical receiver security. So this is really the best we could hope for. And okay, so this is an oblivious transfer protocol, which is very short in the round complexity and very secure. And therefore, it's not surprising it found many applications in the literature. And there are many examples here. So a bit about prior work. So up until recently, we only knew how to construct SSPOT from number theoretic assumptions, which are breakable in quantum computers. And there are post-quantum constructions of SSPOT that were constructed pretty recently, and all of them are from LWE. And what we knew from LPN is how to construct an oblivious transfer, which is computationally secure in the common reference string model. Okay, so let me again repeat the results that we get. So again, we construct the first two messages, statistically sender private oblivious transfer from LPN in the common random string model. And then we show that we can actually remove the CRS using the randomization technique. Okay, so there is a caveat to our work which we should mention, and it is that we rely on the so-called LPN in the low noise regime, meaning that is breakable in quasi-polynomial time. So it could be viewed more as a feasibility result that we can construct SSPOT from LPN. But we should keep in mind that there are also other basic primitives which are only known how to construct from LPN in this low noise regime, such as collision-resistant hash functions. And also there is a potential complexity barrier here. So right now we know, okay, so LPN epsilon, if LPN epsilon implies SSPOT, then it means that LPN epsilon is breakable in SDK. But right now, we only know that LPN in the low noise regime is breakable in SDK. So it doesn't mean that it's not possible to construct, to achieve SSPOT from LPN with higher noise, but it means that it could be harder to construct such SSPOT from LPN with higher noise. It might be harder, and it would break the limit of what we know about the complexity of LPN. Of course, it's a very interesting question raises up here. Okay, so this was the end of the first part of the talk. And now let me dive into the actual construction, and we're going to be a bit more technical here. Okay, so we are starting with the receiver and the sender, and the CRS is going to be consist of a long matrix A and a random vector V over the binary field, of course. And the receiver is going to sample according to the LPN assumption S and E, and it's going to calculate V0, which is going to be equal AS plus E plus C times V. And it's going to send it to the sender. Now the sender is going to set V1 to be the sum of V plus V0, V from the CRS. And it's going to sample two vectors, x0 and x1, according to some sparse distribution chi. And it's going to send, for each bit, it's sending x transpose V plus M, and an additional information in the term of x transpose times A. Then the receiver, for its choice bit C, it outputs the relevant first part of the message from the sender minus the second part multiplied by the secret S. Okay, so why this should work? So let's first talk about correctness. So note that VC, when the receiver and the sender are honest, then VC is just equal AS plus E, and therefore the expression the receiver outputs it just equals, a simple calculation shows that it equals X transpose E plus MC. And because both E and X are going to be sparse enough, we are going to make sure that X transpose times E is going to be equal 0 with high probability. Okay. The receiver privacy follows directly from the LPN assumption because AS plus E looks random to any computationally bounded sender, so it completely hides the choice bit of the receiver C. And regarding sender privacy. Okay, so first let's consider the case of semi-honest receiver, just for warm-up. So note that V1 minus C equals AS plus E plus V, because how the sender sets V1 and V0, and the receiver here is honest. And therefore, the expression that contains the second message of the sender is going to look like the expression written down here. It's X transpose times V plus M1 minus C plus something that is independent of V. And because V is an inner product extractor seed, we get that X transpose times V looks random, even given the leakage X transpose A. And we are going to make sure that this distribution chi also has enough entropy to make this claim. Okay, so we are going to, so chi has to have enough entropy, and it has to be sparse enough. And this is why the protocol is, this is like an intuition why it should be correct. And I want to mention that already here in the semi-honest case, we receive the bound on epsilon, which is going to be equal order of log n squared divided by n, and the calculation shows that this is really what happens here. Okay, so really the construction itself is pretty simple, but the challenge here is when we wanted to prove that the SSP property is correct in the malicious receiver case. So where is the challenge here? So now the receiver may choose V0 adaptively and depending on the seed V. And therefore the extractor argument no longer works. So the question raises up here is, does any adaptively split of V to two seeds, V equals V0 plus V1, contains good extractor VI? And this is because when the receiver fixes V0, it actually fixes such a split, because remember that V equals V0 plus V1. Okay, and what we want to argue is that one of the messages still stays hidden. But it turns out that the inner product extractor is generally not resilient to such linear quantum attacks. We also show a counterexample in the paper, and therefore just arguing that he has enough entropy is not going to be enough. But fortunately, in our case, we have a specific leakage form, X transpose A, and also we can choose the source chi. Okay, so we choose chi in the following way. So chi is going to be the sum of k independent unit vectors we choose Chi like that because it behaves nicely with the Fourier transform. And we summarize n divided by log n vectors. Okay, and after choosing Chi, what we want to show formally is that with high probability over the CRS, for every split of V into two parts, V equals V0 plus V1, there must exist some VI among them, such that X transpose VI still looks random, even given the leakage X transpose A. Okay. But how are we going to prove this? So I'm going to give you a sketch of the proof. All the details are, of course, in the paper. So again, this is just a reminder of our goal here. So what we prove in the paper is the following lemma. And it says that for every matrix A and vector W, the statistical distance between these two distributions is actually bounded by how balanced are all the vectors in the coset A plus W. And we use a Fourier transform to prove this. There is also a formal expression for this state, but I'm not going to dive into the formal expression here. But I'm just going to try and give you some intuition of why this maybe should be true. So let's ask ourselves the other question, and it is when X transpose W is actually predictable given X transpose A. So note that if by chance there exists some vector, some small vector in Hamming weight in the coset A plus W, then X transpose A is actually predictable given X transpose W is actually predictable given X transpose A because X transpose times E star here, which is a low Hamming weight vector, is usually equal 0. Okay. And also, if it happens that there exists some large vector in the coset, then we can still predict X transpose W. And this is because the way we chose Chi, which implies that X transpose times the vectors of all ones always equals to K modulo 2. This is just also a simple calculation that shows this. And therefore, these two observations tell us that we must have that all the vectors in the coset are balanced to have good statistical distance between the distributions. And the lemma shows that this is actually enough. Okay. So now our goal becomes to show that with high probability over the CRS, we can, and for every split of V, we can find some vector for which the coset A plus VI is actually well balanced, meaning that all the vectors in the coset are well balanced. And we prove this using a case analysis. And also we prove the following two lemmas. So first we prove that with high probability, A is what we call the thinly balanced, meaning that for any W, in the coset A plus W, most members are well balanced. So using this lemma, we control most of the balance parameters. But still, we have maybe some vectors which we don't know what's going on with them. But for this, we prove the second lemma, which states that with high probability, V is what we call A balanced for sums, meaning that for every split of V into two seeds, V equals V0 plus V1, there must exist a VI among them, such that in the coset A plus VI, all the members are somewhat balanced. So combining these two bounds together, we get a total bound on the all vectors in the coset, and it turns out to be just enough. Okay, so this is the end of how we prove the statistical center privacy property. And now let me tell you about a few words about how are we going to remove the common random string here. Okay, so we have the SSPOT protocol, which we just constructed. And first, we are going to use a technique by Dwork and Naor of reverse randomization to get some middle results of a protocol where the receiver security holds for every CRS, even if chosen by a malicious sender, for example. And then we show how to transform the middle result to the construction in the plane model of SSPOT. And here we de-randomize the CRS using a PRG that fools non-deterministic distinguishers, which is known to be applied by standard Nissan-Wigderson style worst case assumptions. So the challenge here is that we need an algebraic characterization that captures what we call the bad CRSs, meaning the CRSs that don't have the SSP property. So maybe this set of bad CRSs cannot be efficiently certified, but maybe what we show in the paper is that we can find a bigger set that is still not too big, that is certifiable, and it contains all the bad CRSs. Okay, and then we use the PRG and we have the proof that the PRG contains a lot of good CRSs, and therefore, if the two parties execute this pseudo-random generator and use the outputs as common as the CRSs, then it's enough. And there are more details, of course, in the paper. Okay, so the open questions raises up here is, can we achieve SSPOT from LPN with better noise? Of course, and also how expressive is LPN in the, in the next noise regime, like n to the minus epsilon? Can we build a collision-resistant hashing from it? What about hardness in SDK? And so on. And also, in general, how far can we push this assumption of LPN? So thanks. And if you have questions, so feel free.
Thanks for this talk. Are there any questions?
Hello. So in Azure Crypt 21, we have a paper showing that using ring LWE, it is possible to give a version of the protocol that is much more efficient, and also using.
Maybe can you start over? Sorry, I wasn't. Can you begin again the question?
Yeah. So in Azure Crypt 2021, we have a paper with a statistical center private OT. Showing that using ring LWE, it is possible to improve the efficiency, but also simplify part of the proof using the fact that whenever you have one short vector, you have n linearly independent ones. And so the question is, did you look at whether using ring LPN, it is possible to do something similar?
Actually, we didn't look about ring LPN, so I don't know.
Thanks. So let's thank the speaker again.
Thank you very much.
That brings us to the last talk in this session. It's called Constructive Post-Quantum Reductions, and the paper is by Nir Bitansky, Zvika Bakirsky, and Jael Kalai. And the talk is going to be given by Nir.
Hear me at home? Okay, great. So hi, I'm Nir, and I'd like to tell you about constructive post-quantum reductions, and this is work with Zvika Bakirsky and Kalai. So we're still in the context of post-quantum cryptography. We want to design classical protocols that withstand quantum adversaries. And post-quantum cryptography is something that our community has been studying for a while. And as you know, it has required us to rethink many of the aspects of crypto. One obvious thing is assumptions. We can no longer use assumptions like factoring that are quantumly broken. We have to turn to new sources of hardness like lattices. Another aspect is how the quantum adversary interacts with our classical protocols. But perhaps an even more basic aspect is reductions, right? To the many implications that we proved in the classical setting also hold in the quantum setting. For example, do one-way functions still imply all of symmetric key cryptography? And this is going to be our focus today, reductions. So let me be more concrete about this. So, we typically construct some cryptographic primitive P from an underlying assumption, say Q. And we would like to show that breaking P is no easier than breaking Q. And as you know, the way that we do this is by designing this efficient reduction algorithm that can take any adversary that breaks P and use it in order to break Q, right? And such reductions are really the bread and butter of cryptography. We've been working on them for a while. And it would be a shame if we would have to redo all of these reductions from the classical setting in order to achieve post-quantum security. And then, this sort of raises the natural question of whether we can lift all the reductions that we have from the classical setting into the post-quantum setting. And there seems to be, a good reason to hope that we can do so, because really most of the reductions that we have in classical crypto are what we call black box. We don't really care how the adversary is implemented. In particular, why should we care that it's quantum? These reductions should still work. But it turns out that this question is somewhat more nuanced. And in particular, this is a known problem, say, in the interactive setting. And the reason for that, which is something that Xiao already mentioned in the first talk, is that something very basic that a classical reduction would do is rewind the adversary, some intermediate point in the protocol. And the problem is that in the quantum, we have what we call the observer effect. Whenever the reduction sort of views the messages of the adversary, its intermediate quantum state is disturbed. And now we no longer have guarantee in what's going to happen next. So this doesn't generally work. And as a matter of fact, you can even show examples of interactive protocols where you have a classical reduction to, say, LWE, which is allegedly a post-quantum secure assumption, and yet you can quantumly break these protocols. So we really don't expect there to be a post-quantum reduction, assuming that LWE is really post-quantum secure. Okay, so let's put aside interactive protocols and focus on non-interactive primitives like pseudorandom generators, public key encryption, etc. There are still, of course, plenty of reductions in this setting that we would like to carry over to the post-quantum regime. And here it may seem that things should work, right? After all, the adversary has no intermediate state in the protocol. It's a one-time thing. The reduction queries it with a challenge. It immediately spits out an answer, and that's it. But the thing is that we should be a bit more careful, because what we actually want is we want reductions that would also work if the adversary has some quantum auxiliary input, right? And such auxiliary input could come from different places. It could be the result of expensive pre-processing. It could be some intermediate state in a larger protocol where you're using your primitive, and so on. But the problem now is that we're going to encounter the same difficulty that we just did in the interactive setting, because if we have a reduction that calls the adversary multiple times, then again, the state, this auxiliary quantum state, is going to be disturbed. And after we make the first query, we actually have no guarantee whatsoever on what's going to happen next. Okay, so perhaps there's a simple solution to this problem, which is sometimes taken in the literature, which is why not just supply the reduction with multiple copies of this quantum state, then everything should work perfectly. And the problem with this is that it's not constructive, right? So in general, you cannot copy quantum states, let alone do it efficiently. And maybe in some contexts you wouldn't care about this. Maybe if all that you care about is your underlying assumption Q, and you're sort of willing to assume that it holds with respect to any auxiliary quantum input, regardless of how many copies, then you're fine. But I want to argue that in general, we do care. And what we really want is constructive reductions. And what I mean by that is that we want the reduction to work given the adversary and the same quantum auxiliary input. It shouldn't use any further resources that it cannot generate on its own efficiently. And really, reduction-based cryptography is much about this win-win paradigm, right? We want that if now someone comes up with a concrete algorithm, a concrete way of breaking our cryptographic scheme, it should immediately lead to some algorithmic advance, right? And we should be able to run this algorithm right here and right now. And we're really not the first to argue this. This is also something that is targeted classically, right? This is why we put a lot of stress on designing uniform as opposed to non-uniform reductions. Okay. So another goal on top of constructiveness, which a goal that doesn't really come up classically, is what we call durability, right? Like what we'd like is for our reduction to keep working forever. If someone actually gave us an algorithm that breaks our cryptographic scheme, then now we should have an algorithm that sort of works for eternity. That is what would happen in the classical setting. We don't want it to work only once or degrade over time, and then we can no longer use it. So this is another goal which we call durability. Okay. So now that you know what we want, let me tell you what we actually show in this work. So basically, we show how to lift a large class of reductions from the classical setting to the post-quantum setting. And these are reductions from Q to breaking some other primitive P that have the following properties. So first, the reduction should be black box. This sounds almost inherent for such general lifting theorem. The second thing is that we want the reduction to be non-adaptive, meaning that it generates all of its queries to the adversary ahead of time. And the last restriction is that the primitive P we're reducing to should be either a decision assumption, like say a pseudo-random generator, or maybe a search problem, but with few solutions. And the post-quantum reductions that we come up with are all constructive reductions, and they're also durable. Okay, once you get them, you can sort of use them forever. Now, along the way, we introduced certain intermediate models of stateful adversaries that I think that are interesting on their own, even from a classical perspective, and I'll mention those in a bit. And we also show a negative result that sort of complements the positive result. We showed that this restriction on P, on the primitive we're reduced to, this restriction to, say, decision assumptions, is somewhat inherent. I probably won't have time to touch this today, but you can look at the paper. Okay. So these are the results, and for the remaining time, I want to give you a taste of the techniques. Some of you may already recognize this dog from our video abstract. She's really in charge for some of the techniques in the paper. Okay, so what we do is basically we want to sort of bridge different adversarial models. Our finish line is, what we know. Okay, it's the setting where classical reductions actually work, where you're able to sort of make calls to the same adversary again and again, as many times as you need. This is what we call a stateless adversary. And what we start from in the quantum setting is quite far from that, is what we call a one-shot adversary. Okay, so we have an adversary that breaks our scheme, but it does so once, and once we even make a single query, the state is disturbed. We don't know what's going to happen next. Okay, so this is the gap, and we want to somehow bridge it. And we're going to do this in several steps, and I'll tell you about these steps a little bit. So the first step is what we call transitioning from this one-shot adversaries to persistent adversaries. So what are persistent adversaries? These are adversaries that sort of, they never run out of steam. They keep solving. So perhaps their internal state changes, but the probability that, they break your primitive remains roughly the same. Okay, it still remains high over time. So these are persistent adversaries. And I'm not going to dive into how we bridge this gap. But in a nutshell, we leverage here a recent quantum rewinding technique by Chiesa, Spooner, and Zandri. But I do want to mention that the restriction to decision assumption, etc., already comes up here. But as I told you, it turns out to be somewhat inherent. Okay. So this is sort of the first step. Now we have a persistent adversary. And perhaps before moving on to the next step, we should ask ourselves, why isn't it enough, right? Because now we have an adversary. It's a good, it's a good adversary throughout time. It will keep breaking our assumptions. So, what is missing? And the point is that even though sort of like the set of instances that the adversary is able to solve remains large, remains roughly the same size, it sort of drifts around. Okay, the state does change and it sort of drifts around. It's not really fixed. And this could present a problem for reductions that make multiple queries that could be very correlated to each other. Okay, say like the Goldreich-Levin query, if you think about it. And in the extreme case, it would be that after you make your first query, the state somehow remembers this query, and later on, it wouldn't answer correctly any related query, any query in its area. And then you're in trouble. Your reduction won't really work. Okay, so we can't stop at persistent. We have to somehow move on. And the next model we're going to consider is what we call memoryless adversaries. Okay, so we're not just persistent, we're also memoryless in the following sense. So here, the adversarial strategy is fixed ahead of time, independently of the queries that we're going to make. But it could still be a different adversary at every time point. Okay, you can think about it as an adversary that simply has a clock, but otherwise it doesn't keep any state. So we show how to move from persistent adversaries to adversaries in this model. Basically, we show how to simulate such memoryless behavior in the case that our reduction is non-adaptive. So the non-adaptivity requirement already comes up here. And this is sort of the most technical part, perhaps. In the paper, let me tell you about it, at least in a few words, just give you some intuition. So we want to simulate this memoryless behavior. We want to prevent this extreme event where somehow the state remembers our queries and then refuses to answer correlated queries. And the basic idea is to leverage the fact that, after all, the adversary state is polynomially bounded. Okay, so it only has some limited memory of past queries. And what we're basically going to do, we're going to somehow flood it with queries in a way that prevents it from sort of remembering the meaningful queries. So let me be a bit more specific. So whenever we want to make the ith query of the reduction, what we're first going to do is we're going to sample many dummy queries. Okay, we're going to sample many dummy queries from the marginal of the ith query. And we're going to plant our real query somewhere at random between these queries, and then perform all of these queries with our real query hidden between them to the adversary. And what's the intuition here? The intuition is that the adversary cannot really tell the real query from the dummy queries that come from the same distribution. And because its memory is bounded, it cannot remember all of them. Okay, so that's the intuition and why it could work. And we actually managed to prove that such an execution is delta close. If you look at the query answer distribution that you get, it's actually close to an execution with some predetermined set of oracles. So I'm not going to tell you how to define them. In a word, they're defined only depending on the dummy queries and not the real queries. And to get this closeness, we of course have to make sure that the number of dummies, the amount of noise that we introduce is sufficiently larger than the number of qubits in the adversary state. Okay, so formally this is showing using quantum mutual information arguments. You can look at the paper. Okay, so this is how we bridge from persistent to memoryless, and we're still not at the end. Like the gap is that at the moment we know that at each timestamp we have a different adversary providing us an answer. Where we want to get is we want to have basically the same adversarial algorithm answering all of our queries. That would guarantee that our classical reduction would work. Okay, so this is the last thing that we need to bridge. And here we show another sort of simulation argument. In 2 words, the way that we're going to do this, basically, we're going to answer every query with one of these oracles at random. Okay, so every query we get, we're going to choose one of these oracles at random and provide the answer using that oracle. And here again, we're going to leverage the fact that our reduction is non-adaptive, so we can make this random assignment ahead of time. Okay, you have to watch out for collisions, etc., but it works out. Okay, so this way we eventually bridge the gap all the way to the setting where we can actually apply our classical reduction. Okay. So we constructed all these mini bridges. We bridged the entire gap. And as I said, I think that these models, these stateful models, and also this memory models, are pretty natural to look at on their own, right? You could ask, what can you do when you have an adversary that sort of adapts over time, is stateful? I think these things are interesting, and in fact, these kind of questions were also explored in concurrent work by Chen, Freytag, and Pass. They call it cosmic security. In particular, this last step, this memoryless model, and this last shuffling step is also something that they do there. Okay. So this is mostly what I wanted to say about the techniques and the work, but I do want to leave you with something to think about. So what we showed applies for non-adaptive reductions, and really many, perhaps most of the reductions that we have in classical crypto are non-adaptive, but there are some notable examples of adaptive reductions. Perhaps the most notorious ones is pseudorandom generators from general one-way functions, not say regular or objective one-way functions, but any one-way function, this reduction turns out to be adaptive. Actually, I had no idea. I discovered this recently. It is adaptive. So it's a very basic question. What can you do here? And one thing you can try is, of course, come up with a non-adaptive reduction for PRGs from one-way functions. People have been trying to do this for a long time. Good luck with that. But more generally, can we still do this constructive lifting also in the adaptive setting? Maybe this is a very interesting question. Okay, so this is all that I wanted to tell you. Thank you.
Thanks for that nice talk. Are there any questions in the audience?
What about a situation where there is a random oracle involved, so the adversary uses it, so somehow the reduction has to simulate it to do any of these techniques? Have you thought about that, or do they apply?
Yeah, they won't really work. So this is a different setting. So what we considered is completely non-interactive. You can think about like non-interactive things where there's also some access to an oracle. Let's say you can even sort of random functions and signatures, and this is something that we didn't look at. And there things are sort of challenging because the adversary does inherently has an intermediate state between different oracle calls. And actually, there are some interesting results also on archive or reprint recently. I can tell you about this offline.
Thank you.
Sure.
Any other questions? Then let's thank the speaker again.
Thanks.
That concludes the session on post-quantum crypto. Thanks everyone for staying, and please make sure to bring some warm clothes to the beach. It can get quite cold there.